Hello everyone. So in this video, we will try to discuss the first experiment of the design laboratory, which is your free vibration of a spring and mass system. So the aim of the apparatus is to determine the natural frequency, the time period of the undamped. So this particular system is not damped, it is undamped. So it is a free vibration system of a single degree freedom system. So you have to determine what and all. First thing, you have to determine the natural frequency. Okay. Natural frequency. Then you have to determine the time period. In order to do so, we should require the stiffness of a spring. Okay. In this experiment, you will be just having a spring and a mass system. There will be a spring like this and a mass. Okay. Based on this, we have to calculate what is stiffness, what is the natural frequency, and what is the time period of the given system. We shall see an experimental setup now. Now we will look at the experimental setup of a free vibration system. Okay. So the experimental system is not so complex. It just contains a spring like this, where you have to fix this spring at one end and have to add the weight at the other end so that it extends and you can take your readings. So where to fix? So here is a nut here. So in this nut, there is a small hole where you have to insert this particular spring here and tighten it with a nut. So once the spring has been fixed, what you have to do is you have to take this scale, which is linear scale, and you have to measure the free length of this spring. Length has to be measured from the starting coil to the end coil. You have to not consider the extension supports which is provided for the support. You have to not consider that. Only for the coil region you have to take the length. So for this particular coil spring, so this is your L1, which is your free length. Now the next scenario is you have to add the weight for the spring. To facilitate that, a weight pan is being allotted. So first, initially, this is also contains some weight, is it? So you have to measure the weight of this, note it down in your observation, and then you have to fix this weighting pan for this bottom part of your spring. So for that, again, you have a hole and a nut arrangement, which is the locking system. So insert that particular spring here and lock it with the nut like this. Okay. So once the weight pan has been attached, now we have to add the weights to the system. So as and when you add the weight to the system, the spring starts extending. So as and when you add the weight, so you have to note it down the extension ready. So let us add 1 kg of weight. The different weights will be provided to you, like this is 1 kg of weight, this is half a kg. So first we shall add 1 kg of weight to this. Okay. I have added the 1 kg of weight. So let it settle down for a meanwhile. After it settles down, take this linear scale again and measure the starting coil to end coil, what is your length, and take that particular reading as L2. Now, initial reading was your L1, which was without any weight. Now, L2 is your reading with weight. Okay. So this weight consists of the weight of the pan plus 1 kg. So it is around weight of the pan plus 1 kg. So this is your first reading. If you want to take the second reading, add one more. How much the mass you require? Like I am adding now 500 grams, which is half a kg. Again it extended. So again take a reading. So this is how you have to do it in order to calculate the stiffness of the spring. Okay. So this is how you take the readings for spring 1. So there is another spring which has less stiffness when compared to this particular spring. When you are looking at it, you can understand it. So similar procedure has to be followed to take the readings for this particular spring. Detach this spring and attach this spring, fix it at one end. Again add the same support, weighing pan and the weights, take the same readings. Okay. So this is one part of the experiment. The second part of the experiment, you have to calculate the oscillations. So for basically you can fix it for 10 or 20 oscillations. So basically you take for 10 oscillations. For that 10 oscillations, what is the time taken? So you have to use a stopwatch like this. Okay, just hold a stopwatch in your hand and give a forcing function to the spring mass system like just listen. So for 10 oscillations, what is the timetable you have to measure? That is your reading. So this is for the free, without any mass. Now we can add the mass. Okay, similar procedure. Now we can add the mass of 1 kg. Okay, again take your stopwatch. Now apply the forcing function. Just pull it a little bit and leave it for the 10 oscillations. What is the time taken? So carry it down for that we have another spring also, which is this. The same oscillation has to be taken for this also. So this completes the gains whatever you take from the experiment. Consider. So once you have finished your experimentation, you will be obtained with the following readings. The mass of the pan being 0.518 kg. The initial length of the spring is 0.1. You have to take it in meters. Okay. Now, the mass of the attached to the spring, so first one being 1.018 and second one being 1.518. So for that corresponding masses, these are the deflections which I have noted down in terms of L2 with the meters as its units. Now we shall proceed with the calculations now. Okay. So now we have to find the deflection. So deflection is given by L2 minus L1. So L2 is nothing but your final. Once the mass is being added, what is the deflection? That is your L2. L1 is being the initial, which is the free expansion of the spring. So let us substitute for the trial 1. Now I am calculating it for the trial 1. Okay, for the trial 1, it is L2. So I will just highlight it like this. So this is your trial 1. Okay. So L2 is 0.115 minus L1 is 0.1. So delta 1, that is for the trial 1, is how much? It is 0.015 meters. Okay, so this is your delta 1. So note it down. Back here it is 0.015 meters. Okay, next thing you have to calculate the stiffness. Okay, this is the value of K, which is given by M divided by delta, that is mass divided by deflection. So for the first trial, which is K1 is equal to, mass would be how much? 1.018 divided by delta for the first trial is 0.015. Okay, so if you calculate this, see, mass is in kg, okay, and delta is in meters. So whatever you get the value would be in what? Kg per meter. So 1.018 divided by 0.015 leads to a value of 67.86. Okay, so this is your value of K1. Similarly, so first you enter back this. So it is how much? 67.86. So 67.86. Enter back in the tabular column. Now similarly, you can carry out the calculations for the second trial, which is this. Okay. So you would get delta 2 around 0.025 and K2 around 60.72 kg per meter. This is in meters again. So the values you enter back into the tabular column, it is 0.025 and the stiffness is around 60.72. The unit is kg per meter. So the last thing you have to calculate is the mean stiffness. The mean stiffness is given by Km is equal to 9.81 into, see, here you have K1, K2, K3 divided by 3. Why? Because they have opted for 3 different readings. Now we have taken only 2 readings. So you can just take an average of those 2, that is K1 plus K2 divided by 2. Why 9.81? Because we are converting the kg into Newton. So the kg would be converted into Newton you have substituted in meter, so it would be Newton per meter, whatever answer you get. So just substitute the values. 9.81 into K1 is equals to, what is K1? It is 67.86 plus K2 is 60.72 divided by 2. So if you calculate this, your K1 value would come in Newton per meter because you have multiplied with 9.81 and it is around 630.68 Newton per meter. So this is your final answer. So Km, the mean stiffness value is around 630.68 in Newton per meter. So this is one part of the calculation. The second part, you will be calculating the frequency and the time periods. Okay. So in the second part of the calculation, we need to calculate the time period and the frequency. So for that, we will be disturbing the spring mass system and you will be noting down what is the time required for the 10 oscillations from the experimentation. So these are the readings which you have got from the experimentation. Now we shall solve for the first trial. So for the first trial, the experimental time period is given by T divided by N. T is nothing but the time required for the 10 oscillations. So N is, you have taken number of oscillations to be 10. So what it is, T is 7.91 divided by 10 oscillations. So it is around 0.791 seconds. Okay, just note it down back here. So it is 0.791 seconds. Now similarly, you have to calculate the theoretical time period. So theoretical time period is given by 2 pi into square root of m divided by km. So km you have calculated in the previously, which is this value that is given by substituted. Mass is around 1.018 divided by km value is 630.68. So the obtained value for the T theoretical is 0.2524 seconds. So this is your T theoretical. Okay. So substitute back, it is 0.2524. Similarly, you can calculate for the other reading, which is this. Okay, so you can use the same procedure for calculating the values of this. So it comes around 0.422 seconds and this comes around 0.3082 seconds. Okay, now for the spring number 1, continuation for this, now we have to calculate the experimental frequency and the theoretical frequency. So experimental frequency is how will you calculate the experimental frequency? It is just the reciprocal of, so F is nothing but it is the reciprocal of the time period, is it? So if you want the experimental frequency, then you have to reciprocal the experimental time period. Okay, so if you want the theoretical frequency, then you need to reciprocate the theoretical time period. So whichever you require, you can just reciprocate it. If you reciprocate, you will get around, so theoretical frequency for the trial 1 is 3.96 hertz. Okay, so this is the theoretical one, 3.96 hertz, and the experimental frequency is 2.56 hertz. Now we have to calculate the difference between these two. So percentage difference is given by this particular formula here. You can use this formula. So how will you use? So F theoretical is 3.96 minus F experimental is 2.56 divided by F theoretical 3.96 into 100. So if you do so, you'll get the answer in percentage, which is the percentage variation. So that is around 35.6%. So you can carry out the same thing for the other reading also, which is marked in blue color here. You'll get around experimental frequency as 2.36 Hertz and the theoretical frequency as 3.24, with error percentage being 27.16%. So this completes the overall calculation of your experiment number 1. Okay.